Welcome to this talk about without resilience, nothing else matters. Let's see. So how many of you would like to go to production with an application that is like beautiful, responsive, scalable, highly concurrent, scalable, resource efficient, loosely coupled, yada, 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 yada? Raise your hand. I guess, yeah, we all do, right? But guess what? The problem is that nothing of that matters, not the slightest, unless your app is actually available, unless it's actually up and can serve requests and can fulfill its purpose, right? So really, without resilience, nothing else matters. So I think it is really at the core of everything we do, and I think it's something that we have hand-waved way too long as an industry. In this talk, I'm going to try to get down to the fundamentals of resilience. I mean, look at some examples how other sort of fields like nature, biology, social systems, and so deal with resilience, and see how we can learn from that and apply that to software systems. Okay. Most of you probably recognize this picture. It's from this movie Rocky, and it's about this. If you don't know about the movie, the short plot is about this underdog. They call him the Italian stallion. He gets a shot at the title, and some of you might remember this quote, right? But it ain't how hard you can get hit; it's how hard you can get hit and keep moving forward. How much you can take and still keep moving forward. That's how winning is done. And this is what I call fault tolerance. It's about getting hit, hopefully survive, you limp along, hopefully enough that you will win. Unfortunately, Rocky didn't do that in this movie. Later movies, he actually took the title. But the problem is that fault tolerance is not really a sustainable strategy. It's actually very well illustrated in this movie, and because what I believe that we need is resilience, and the resilience is beyond fault tolerance. I'm going to dive down in what resilience really is, what it really means, why I think it's needed, as I said, how other industries and fields of science are dealing with it, and what we can learn from that. So what is resilience? According to Merriam-Webster, is defined as the ability of a substance or object to spring back into shape, the capacity to recover quickly from difficulties. It's really about being able to restore full functionality, not just to limp along like Rocky and hope for the best, but actually like fully self-heal and come back to where you were before you got hit. And there's even a lot of sort of discussions nowadays about anti-fragility. That's actually beyond resilience, being able to grow stronger when you get hit. I'm not going to talk about that here. I don't think it's as concrete, and we are not really ready for that as an industry yet. We're not even able to build truly resilient systems yet. So I'm going to focus on that here today. And software systems today are incredibly complex. And here, this is just a couple of diagrams that have been circulating around the internet the last couple of months. And I really believe that since software systems are so incredibly complex, we need to study resilience in complex systems. But what is complex? And how is it different from complicated? Some people, including myself some time ago, actually confused the two terms. Okay, so this is a complicated system. I just love this GIF, actually. I was really happy when I found it, because it's a great illustration, of a complicated system, because a complicated system consists of many small parts, usually all different, that with each one has a precise role in the machinery. And they together work in some sort of cohesive whole. And it's usually possible, however very hard, but usually possible to fully understand a complicated system if you really Put your mind to it. A complex system, however, is made out of very many similarly interacting parts with simple individual rules that together lead to emergent properties and where their interactions and how they work together produces a globally coherent behavior. It's actually, by definition, impossible to understand a complex system. You can only try to understand it by simplifying it and breaking it down into the individual components and individual rules. Okay? So this is an example of game of life. You see, I mean, in isolation, it's very easy, predictable even, right? But once you start putting things together, even though it's extremely simple, it immediately starts to producing behavior that's almost impossible to understand. And it's very important to understand that the complicated is not equal to complex. And one of the most fundamental wisdoms I got when I did some research, I found when I did research for this talk was from this paper and this quote by Richard Cook, where he said that complex systems they run in degraded mode. Complex systems always run as broken systems. Okay? In a non-trivial complex system, something is always failing somewhere. It is a fact of life, and that drastically changes the way we should approach the problem, as I'll try to outline throughout this talk. And we as humans, we generally just makes it worse, a lot worse. This quote is from this systems thinking expert, Donella Meadows. She writes about points for human intervention in complex systems. And I quote, "Counterintuitive. That's Forrester's word to describe complex systems. Leverage points are not intuitive, meaning points where we interact with the complex system. Or if they are, we usually, as humans, intuitively use them backwards, systematically worsening whatever problem we are trying to solve. Humans just makes it worse. And I think we really need good models to understand complex systems and how failure happens in complex systems. Okay? What happens and what we can do about it. And we're always operating at the edge of failure, really. I got this illustration, this sort of way of thinking, about the psychological and human part of failure from Richard Cook as well. He did a great talk and had written some papers on this as well. So this model that was actually defined by his colleague Rasmussen in '97. By the way, Richard Cook is an MD. He's been doing studies of resilience systems in medical systems for 20 years, which is, I think, it's very interesting to get like a different perspective on what failure and what resilience really means. So in this model, we have three different boundaries. First, we have the economic failure boundary. Okay, you have to stay within this boundary, else you go out of business, essentially. Then we have the unacceptable workload boundary. If you cross this boundary, then you fall asleep, or you burn out, or so. People can't perform useful work if they cross this boundary, essentially. It happens, in battlefield situations when shipping 1.0 at startups, people actually literally fall asleep doing what they're about to do. And then we have the accident boundary. If you cross this boundary, then you fail, for some definition of failure. Okay, it can be like, you can define it in many different ways. No outages, no one dies, no business is lost or so. And then you have what is called an operating point that moves within these boundaries and is always moving, constantly moving around. And there's some lag here, that's why I'm looking back sometimes. If you cross the accident boundary, that's when you have a failure. That's when you have some sort of outage, okay? And then we have three different pressures. The first pressure is the natural pressure for economic efficiency. Management always wants to reduce cost. They want to try to push the operating point away from the economic failure boundary. We can't go out of business, and so on. So that's a natural tendency to push it away. And there's also, as humans, we have a natural tendency to try to push this point away from the unacceptable workload boundary, because we're lazy as nature. We want to go home to our kids or do something else, right? So there's a natural tendency to just start pushing the operating point towards the accident boundary. And then if we have an outage then everyone panics. Wow, I didn't expect that. We start perhaps rewriting the software and bringing in new tools, turning on WebLogic clustering. No, you shouldn't do that. New policies, training, I don't know, stuff like that. And that sort of pushes the operating point away from the accident boundary again. But then, life arrives, life comes back, right? And it's sort of, and then after a while we forget about it, and these two massive forces are starting to push the operating point again towards the accident boundary, and then we have an outage, and then we repeat, right? So the question is, why don't we have failures all the time? You should expect this sort of drifting to happen all the time. It's because we add usually intuitively what is called an error margin, or a marginal boundary. That we say we shouldn't cross this because it feels like then we enter risky territory. Okay, and this error margin is usually defined by rules. It can be speed limits on the road. It can be we shouldn't use more resources than X, or we shouldn't allow more users than Y, or Victor was just talking about back pressure in queues and in streaming. You define your boundaries and say we shouldn't cross these because that means that we're risking failure essentially. So the question is that if we then have this error margin and try to not cross it, why do we continue to have failure all the time anyway? And here's where the interesting psychological effects happen, I think. Because we know a lot about the marginal boundary, right? Because we have defined it, but we know very little about the accident boundary. It's very fuzzy. Okay? So it's not really until we actually cross the accident boundary that we know where it is, and then we take a note of that, and we take a step back, right, and to the beyond the marginal boundary, and hope for the best. Okay. This constant push towards economic efficiency, means that we are forced to or want to constantly try to cross the margin. And so what we usually do is we try to cross this, and then we come back. And then we try to cross again, and then we come back. And after a while, we've been crossing it so many times, and it feels like nothing really bad really happened. It might be okay. We have been operating this way, in and out now for 6 months. Why don't we just move the boundary then? So sorry, I'm a little bit behind on the slides here, but... So this is what happens. So then we just say, okay, since we're operating this way, we should just move the boundary. And we sort of start to moving it closer and closer and closer to the real accident boundary that we don't really know where it is until we have a failure and we're back, right? And this is what's called flirting with a margin. Diane Vaughan wrote about this when she analyzed you remember the Challenger accident, the rocket ship that blew up. This is actually exactly what happened. People that were flirting with the margin, and sort of the real sort of proper name for it is normalization of deviance, if you want to look it up. This is really psychological effect that happens to us all the time, and it's something I think we need to be aware of. And so, since software systems are so incredibly complex, and complex systems always run as broken systems, and we are always operating right at the edge of failure, I think we need to learn to embrace failure. Fully embrace it and learn to design from failure from the start. Find a better way of managing it. And I think that's the most fundamental lesson in this talk that I'll try to make across, rather, that resilience is by design, truly. There's nothing that you can just bolt on afterwards. There's nothing you can hand wave any longer. It needs to be part of the design from day one. Really, I believe that failure is actually a natural state in the application's lifecycle. Calling them exceptions, like we do in Java and Scala and C++ and so, is actually wrong. There's nothing exceptional about failures. It's a natural state in the application lifecycle, and if you embrace to look at it like that, then there's nothing scary about it. If you have a state machine, you have start, suspend, resume, reboot, whatever it is, stop, and fail. So once you get into the failure scenario, you know exactly how to get out of there, because it's already expected. so to speak. This photo, I think, is extremely powerful. It's actually a photo from a home in Gilchrist, Texas. It was designed to resist the floodwaters, and it was one of the few houses that survived Hurricane Ike in 2008. It's a house that was really designed for resilience from day one. So in this talk now, we want to look at some patterns, strategies, how to manage failure and to really embrace it at its core. And we're going to start by looking at how some other industries are dealing with it, or fields of science. So biological systems. I just love meerkats, and I learned this very interesting story from a TED talk actually by Nicholas Peroni. You should look it up if you're interested. He talked about complexity theory. And this story is about meerkats and resilience in the animal kingdom. Okay, so meerkats, they are, apart from the sort of being pretty funny and cute, they are extremely social animals. They have very rich social behaviors. And one thing is, for example, is that it's only the dominant couple in the group that is allowed to get babies. All the other ones should be servants, like babysitters, and look after the kids while the parents have fun, I guess. Sounds quite nice. And in this experiment, GPS sort of trackers were put on these meerkats, and they were observed moving from one feeding place to another. And there was a road in between these feeding places that they had to cross. The interesting thing was that it was the dominant female that led the group to the road. Once she reached the road, she stopped, and she gave way to the subordinates and let them try to cross the road to see if it was safe. Like if they got hit by a truck or something, I mean, apparently it wasn't safe, but she could remain safe and wait until the right moment and then cross the road. And the interesting thing is that nature has sort of developed this way of dealing with failure and resilience for thousands of years. You know, the dominant female is extremely important to the group. If she dies, the whole group is really at risk. And this way of sort of giving way, delegating dangerous work to subordinates is something that I think we can learn a lot from when building computer systems as well. So I'll get back to that later. And also, as Nicholas Peroni sums up in his TED talk, nature actually used complexity as a strength, right? He said, and I quote, "In 3 words, in the animal kingdom, simplicity leads to complexity, which leads to resilience." So I think embracing complexity in the right way, I think really can help improving resilience. Another example that I have is from resilience in social systems. We as individuals, we live like this all the time, right? We don't think about it. This is how our society is built up. That for each individual, I mean, you can categorize it that there are 6 ways we can die. Okay, we can die from being too hot, too cold, from hunger or from thirst, or from illness or injury. And there are like 3 sort of categories of essential services that protects us from dying, essentially. Shelter, that protects us from being too hot and too cold. We have supply for stuff, resources, that's for hunger and thirst. And then we have safety, that's against illness and injury. And these services are then laid out in different layers to protect us from dying. So we have you can probably find more, but in this paper, they categorize 7 layers of infrastructure, layers of protection that protects us individuals from dying, essentially, by providing these services. And these are like starting from the top. We have the world, then we have like markets, energy markets, food, fuel markets. The country, you have stuff like the military. I mean, regional. We have the police that protects us. You know, we have in the city we have things like hospitals, water plants. Neighborhood is getting in like closer to the individual. We have things like food shops and stuff. And in the home, we have like heating, we have like a house usually, toilet, tap water, the refrigerators and stuff, and then all the way down into the individual. Without all of this, we will easily suffer from death from one of these ways to die. And this is really how the world works. So we have this sort of these layers of defense, right, protecting us as individuals. We don't think much about it, but it's actually a great model, I think, that we should think about when we design software. And I'll get back to that later as well when I talk about what I call the onion layer resilience or onion layer fault tolerance. So in general, what can we learn from resilience in biological and social systems? By the way, all these stuff I'm talking about here are from papers that are referenced at the end of the talk. I'm going to publish the talks online if you want to dive into more of the details or want to just check the facts. So the first one is that we can see across both of these is that they feature diversity and redundancy. Generally, component systems with a lot of components have a lot higher chance of surviving because it means that failed components can be compensated by healthy components way more easily, right? So they give sort of an insurance effect. Don't put all the eggs in the same basket, as people say. These systems are also extremely interconnected in some network structure, extremely rich, where you have a wide distribution across all scales, and they also have the capacity to self-adapt. Perhaps hard to write systems like that. I mean, to some extent, we can do that through feedback control systems, and so on. And they have an ability to self-organize, to take hits and then learn from that and move on stronger. So this brings us to resilience in computer systems. Unfortunately, we often react like this. First not at all, and then with complete panic. And I really think that we need to fundamentally change the way we think. As I've already said, failure is inevitable, it's natural, it's nothing exceptional. Let's embrace it and try to find a way to manage it instead. And you might have heard about the let it crash philosophy, where something that's sort of was popularized by Erlang and also that we use in ARCA. Actor model for the JVM and so on, and it's really that sort of philosophy is based upon essentially two pieces, right? They're all defined very well by these papers by Candea and Fox. The first paper is called crash only software, and it's a very simple idea. Is that stop is crash safely, and start is just recover fast. If you look at the world like this, then you can always fail and get back on track right away. Okay, it can help you with. Usually, a lot of problems lead to sort of state being corrupted and stuff like that, and that can definitely help with this. It's sort of a sledgehammer, kill the whole thing and reboot, but it's a very useful one. But in a follow-up paper, these guys, Fox and Candea, they talk about applying this idea recursively. The paper is called Recursive Restartability, turning the crash-only sledgehammer into a scalpel. That's really what it is. It's like looking at the world like if you built the system ground up with crash-only components that can fail recursively up, then you have a system that has the ability to really gracefully tolerate failure at many different levels, all the way up. And another interesting paper that I love is one called Out of the Tar Pit by Mosley and Marks. And here they define. They have a good way. I think a good way of categorizing state. Most failures usually are related to state, some sort of state. Like we have inconsistent state, partial data, wrong data, the lost data, duplication of data. It's usually something related to data. Stateless services are a lot more pure stateless services. Not like the faking stateless services, like we have a stateless component and it talks to a SQL database. That's not stateless, really. That's just a misuse of the word, in my opinion. Anyway, so they classify state in two categories. We have input data. That's really the critical data, the data that we just simply cannot lose. That's data that our customers gave to us. Hard to go and ask them again. Can you please fill in the form again? We lost it, right? And then we have derived data. That's data that's derived from the input data. That's stuff that's recomputable, and that's okay to lose. I usually have a third category that I call scratch data. It can be data that's made up, that you make up, that if you lose. It doesn't make much sense, but that you use during computations. That's like data that is meant to be thrown away. when you were at school, you were doing some calculations, and like on the like back of the napkin, and then the result matters, but not the actual way you got there, really. So now let's look at traditional state management. How most systems today, I think, unfortunately, are written. The legend here is that we have the white circle here is the client, and then we have the blue one is an object in the system, and this squared red square is like a critical state that needs protection, state that we just simply cannot lose, or we will look really bad in the eyes of the customer. Okay. And now we have like a lot of this interconnected objects, in some system. And let's say now that a client comes up and he makes a request. By the way, this dotted line here, that's the thread boundary as well. That's also very important, because that I will come back to why it's important, but I can give you a hint. Isolation of failure. That's why the thread boundary is important. Okay, so usually what's happening here is if the client then does it, so I'm getting ahead of myself, sorry. Oh, anyway, I spoiled the whole animation. Sorry. Anyway, what I was going to say, that if you have this synchronous dispatch down and a failure happens at the bottom, if it's synchronous dispatch and you have one thread boundary all the way down, you're going to blow the whole stack all the way right up in the face of the user. That's not a good place to be. First, you're taking down, you have this like cascading failure, taking down a lot more components than necessary. If you have synchronous RPC, added distributed systems like most systems are today, you can actually start taking down multiple machines. I've seen that happen way too many times. The problem, is that, so how should the client react to this? That's hard. And I really believe that this whole model is like utterly broken. I'm sorry to say, but I really think it is. The problem is that, this is the failure management that we've grown up with in Java, C++, and JavaScript and so on. And the problem is that we're giving it one single thread of control that we need to do all the work in. And if that sort of context blows up, then we're screwed, because that's all we got. And these so-called exceptions, they're not true messages that we actually can redirect wherever. They can just go one way, and that is across your call chain. And this means that since this context is the only thing we have, we need to protect that with our life. That's why we need to go around and add try-catch statements everywhere in the code, because things can go wrong almost everywhere. So there are red boxes all over. And this means that, our nice business logic get completely tangled with error handling all over the place. And it's really hard to make sense of it. And it's also extremely brittle. And I think structure here can give us some sanity back, really. And as Sidney Dekker said, accidents, they come from relationships usually, not broken parts. So the relationships need to be loosely coupled. They don't need to be broken up, or you will take down your whole application. In my view, the requirements for a sane failure model is that failures, the first need to be contained, not leak without you want it to. Right? They need to be reified as messages, like sort of material, wrapped up as messages, regular messages. They need to be signaled in an asynchronous fashion. Because if you can signal them in an asynchronous fashion, that means you can do that safely. And they need to be able to be observed, not just signaled randomly, and there needs to be someone there to actually observe the failure. And they need to be able to be managed outside. And if you have failures as messages and asynchronous boundary between these, that means that a healthy component can just sit there and just watch what happens, get the failure message and act. That's not the case, right? If you have like these cascading things, like then it's panic, death. Sorry about that. So first we need to find a way to contain the failure, and once again, right? Here we can learn from other industries. The ship construction in ship construction, they've used this for a long time. They call it the bulkhead pattern, or they call it bulkheading. It's about, the key here is about compartmentalization, like have safe compartments. As you can see here, you have this ship, and you have like compartments. That means that if you get a failure, if you get a hole, or you hit an iceberg, like rips up 3-4 of these, the ship remains still healthy. It can just continue to sail because you have like boxed it. Okay, and when I sort of bulkheaded it, right, and people always bring up, what about the Titanic? This doesn't work. Titanic actually did everything almost right, but not all the way, because in the Titanic, these walls didn't go all the way up to the ceiling. So when enough compartments were ripped up, it started to tip, and then water started to move, like flood over to one healthy compartment, then to the next, to the next, to the next, to the next, and the whole ship sank. So it's actually an excellent example of cascading failures. Don't do that. Isolation needs to be rock solid. Okay, but I think so this way of achieving fault tolerance is good. But yet again, fault tolerance is not where we want to be. We want to build resilient applications. So I think we can do better than this. Actually, we don't want to continue sailing with like these 3 open compartments, right? We need to fix them, heal them as well. And in order to do that, we need to add a way for like some failures to be notified from a healthy context. This is what I call supervision. Okay, so again, failures need to be contained, as we've already seen. They also need to be signaled, observed, and managed by a healthy component. And this supervisor then should have sort of the power to fully manage the failed component. Restore him, resume him, restart him if needed, to restore full functionality and full service. The true definition of resilience, if you remember. So I'll try to explain what this means through an example here of a vending machine. Okay, you might have seen this. I've given this example before. So let's say you have this vending machine, the coffee machine in this case, and we have a programmer who's really eager for coffee, and he walks up to this vending machine. He inserts, let's say, for example, that this vending machine accepts 2 coins. 2 euros is too much. 2 cents is too little. I don't know. 2 Swedish kroner. And the guy puts in 1, okay, and he puts, give me my coffee, I'm dying here, and then really what should happen, and what usually happens is that he gets a notification saying, please add more coins. You haven't fulfilled your part of the contract here. It costs 2. You just gave me 1, okay. And okay, then he puts in 1 and 1 more, and he gets his coffee, and he's happy. Okay, this is what we expect. Then the next day he comes in, he inserts 2 coins, and now he gets an out of coffee beans error thrown in his face. Like, there's no more beans. Where should I find the beans, right? Is it behind the coffee machine? Should I go and open up some I don't know, some storage somewhere? No, I mean, this is not how it works. This is not the programmer's responsibility to deal with the failure of the machine, right? He's just a consumer. So what's going to happen? I don't know exactly if it is what is happening, but in an ideal world, what should happen is that this failure should go to some sort of service guy, like runs around the floors and fixes these machines, right? To the beeper or something like that, and he can come in. It's enough. We need to pour up some more coffee, or fix the grinder if it's jammed or something like that. So in this case, he adds more beans, and the programmer gets his coffee. That's an ideal world. I really think this is the way we should design software. And my point here is that, where you have the protocol with the user. If the user is not fulfilling his part of the protocol that you have defined, then he should expect to get the validation error thrown in his face, right? Because that he can first do something with. He can understand, he can fix it, and he can continue. Right? But an application failure that's happening down some third-party service is down, the database, I don't know, the disk is full, I don't know what it is, right? That's not the client's responsibility, and that should not be thrown in his face. That's madness, right? What should he do with that? That should go to the component that sits and watches the other one. And so this service. It's usually the component that created the service. If he created, he better knows why, right? And he might have split up the service in multiple components, right? And you join on it afterwards or something. I don't know. But it is the component that created this service that's responsible for dealing with the failure of it. And once again, this needs to be built in from day one. It's a natural state in the application's lifecycle. In this service lifecycle, failure is natural. It should be part of the protocol between the creator and the service. So, also in this sort of out of the tar pit paper, they have a lot of great ideas here. They define what they call an ideal system. Okay, you could argue about that, but they have some interesting ideas here anyway. So they talk about essential state. Essential state is the foundation of the system. It's completely self-contained. It doesn't depend on anything. It's just the box where we put the critical state. It of course has some sort of protocol to interact with it, but and then we have then they describe that the next layer is what they call the essential logic. This is sort of the heart of the system. And that depends on essential state, not the other way around. So there's an important dependency graph here. This is usually what we call the business logic, right? And then we have what they call accidental state and control. And this is the least important part of the system, right? This is where data comes in. You perhaps do some computation on scratch data and so on, passing it into the essential logic. But the really important thing is the dependency graph here. So I think what this describes is what I call onion layer state management. It's also called the error kernel pattern. And the idea is that instead of having this state scattered across the whole application, we put it into the innermost center of this onion. And then we have each layer in the onion provides levels, like a level of defense, protecting us from bad things happening. So the key idea is that the error kernel never ever performs a dangerous operation himself. He always delegates that, and then he can assume that he can delegate it in multiple levels. So if one of the outermost layers fails, that's fine, right? Because the critical state is still preserved, and he can continue to try to delegate it again. Perhaps delegate it on another machine, or another service to take over, or something like that. But as soon as a request hits the error kernel, the innermost, we can assume it to be healthy. We can assume it to be harmless, so to speak. Okay, we can always assume correctness. So, in onion layer state management here, what we do is that we put the critical state inside what we call then the error kernel. And then we have sort of levels of defense, as I said, with these components through supervision. So the error kernel creates a bunch of workers for him that might create a bunch of workers for them, and so on. So we have sort of delegation like this. And now, and also, one of the most important ideas here is that each one of these components run inside its own thread boundary. So you can actually die without anyone noticing, which by itself is a bad thing, right? But that means that it can live and die and be restarted in full isolation. And then if you then add a way of signaling failure, you have a way of managing that safely. Okay. So now, if a client comes in and he makes a request, and it goes all the way up to the second layer, and the second layer fails here. I mean, his supervisor will be notified. That is sort of this red arrow. He can deal with that safely. Perhaps through restarting the component, and the component can continue the request and serve the client. In an ideal where the client shouldn't even know. It might take a little bit longer. If the service is down, you might need a timeout and so on. But the client should, in an ideal where, not even know that the failure happened. It's not his responsibility. He shouldn't have to care. If he fulfilled his part of the contract in the first place, of course. And I don't know if you remember the meerkats. This is exactly the lesson we learned from the meerkats. Delegate dangerous work to subordinates, so you are fine. It's fine if others run out on the street and gets hit by the road, or gets hit by a truck, right? As long as you're fine. And this is also the way we learn that social systems, actually the world we live in is actually already architected naturally. That you have these levels of defense, you know. There might be, you know, I mean, sure, I mean, there are situations, of course, where none of this matters, right? If the whole world is blown up in a nuclear war or something like this, but normally, these levels of layers of protection make sense and allows us to stay healthy and not having to worry much, right? So I have 20 minutes. I was planning going through a short example, but I probably. Let's see. I was just gonna show you what an actor is, but that's sort of okay. I might have time for this actually. I'll ask you. Would you like me to be practical now and dive into some code? And show you how this can be done in real code using in this case my top choice is ARCA, or do you want me to continue to stay a bit more high level and talk about how we should extend this model throughout in distributed systems and so on, because I don't think we have really the time to do both a deep diving code and okay I can what. Okay, raise hand. How many would like to see me do some live coding for the first time in years? I'm so freaked out, so hopefully you will not know so many will raise their hands. Okay, and how many would like to continue then talking about? It's about half. Okay. Okay. You decide. Code. Okay, code. Crap. Yeah. Anyway. I'll post the slides afterwards, so I need to mirror. Oh, what's happening here? This is not what I had planned. That's funny. Okay, so let's say here that let's create a new file here then. We call it demo. Actually, I'm going to show you. In Scala, I'm going to see. I'm going to first open it up. I'm going to show you an example here in ARCA. And first, I can just explain a little bit what ARCA is. ARCA is sort of a toolkit, a runtime for building actor-based systems, distributed systems, and concurrent systems. And the reason why I'm going to use it now as an example is that it has a built-in failure model that maps very well to what I just talked about. It's shamelessly stolen from Erlang. I owe a lot to Joe Armstrong and his amazing work there. There are actually links at the end of this talk talking about that. I really believe this is the best way of dealing with failure management. And actors can be it's extremely lightweight object. It is an object that has a mailbox. You can send a message to it. All messages are sent asynchronously. They end up on the mailbox, and the actor then takes and works off this queue one by one. So each actor is fully thread safe. It's like this island of strong consistency, you can say, in this sea of non-determinism, concurrency, distribution. Messages fly around. As it enters the actor, you can assume correctness. You can assume that it's a safe world to live and breathe and operate in. Let's now. Sorry. I need to have first a package, right? Package demo, and then I need to have some imports. So what I'm going to do now is I'm going to illustrate this coffee machine. Okay. So let's start by creating an actor here. And actor is you create an actor by saying extends actor, and then it can have some state. It can have some vals. Actually, this is Scala code. I can say first, I'm using Scala because I'm most comfortable with Scala, but it has a top-notch Java API that's on par with Scala if you want to use it from Java, and everything looks almost the same. It's like slight syntax change. Okay, so the state here is that it keeps track of the number of currently inserted coins. That's sort of my session, so to speak, like 1, 2. 2 should give me coffee because the price is 2. Then I also have this like flag that says that am I out of beans or not? Yes or no. And then I keep in track of my total number of coins. Okay. So I'll get back to this, but I also want to create my coffee manager. This is sort of what I call the service guy. That's the guy that creates coffee machines, manages them. In ARCA, every time you create an actor, you are his supervisor by definition, and you manage his life cycle. Okay. So what this guy does is actor of is a factor method. He creates a coffee machine by passing in this class, giving it a name. Out here comes an address to this coffee machine called, in this case, machine. It has type actor ref, and to simplify, it doesn't make sense in the real world, but to simplify, this coffee manager is the voice what the user interacts with. And for every request he gets for a new coffee or putting in coins or whatever, he just forwards them to the machine, essentially. In the real world, that doesn't make sense. You probably use the machine directly, but bear with me for simplicity here. Okay, and then we have an app that's a driver. Okay, and what I'm doing is I have some stuff that I'm setting up here. First, an actor systems. Carl Hewitt said, like, one actor is no actor. Actor comes in systems. They always interact. That's where the interesting things happen. So we have an actor system here, and we create this coffee machine manager. That's our coffee machine. And then we have a customer. A customer in a real actor system should be also an actor. But in this case, I'm using a testing construct from ARCA called inbox that makes it easier to interact, essentially faking that this customer is an actor so it can send and receive messages, okay? So in the first test run here, what I want to do here is that I would like to be able to put 2 coins into the coffee machine. Once I'm done that, I want to say the selection should be espresso, and then I should wait 5 seconds then to get my beverage. It needs to brew a little while, I guess, and then I simply assert that I got my espresso. Okay, but as you can see, I haven't defined my messages yet, or my protocol, because this is the protocol with the customer. Okay, so what I'm doing here now is that I define my different coffee types. And this is essentially my protocol. I can send coins, the number of coins. I want to have a selection of latte or something like that, and I can also trigger an out of coffee beans failure from the outside, also for simplicity, so I can actually emulate failure. And if everything's go well, I get my beverage, or the protocol says that if I haven't fulfilled my part of the contract, I'm getting not enough coins error. Actually, I do distinguish between errors that are user manage like that's the user responsibility, and what I call failure, that's the application's responsibility. Okay. So now let's implement this protocol in this coffee machine. Then, so the first thing I'm doing is that I say whenever I receive, this is Scala code. It's like a little bit more like more advanced switch statements, essentially. It's called pattern matching, if you don't know that. So in this method, if I receive a coins, then I coins message. I get the number coins, and I increment the number of inserted coins. That's my current session. The total number of coins that's in the machine, and I just print that out. And I also, there's one more thing, as you see, I need to do. I need to make sure that I respond to the selection message as well, right? Because that's my protocol. Sorry. My protocol is twofold. I first put in the coins, and then I'm pushing the button for my coffee. So in here, what I'm doing is I simply first check, have I inserted enough coins? If not, then I'm using. This is actually the way I'm sending a message. I'm taking an actor ref. It's an address. In this case, it's the sender, the guy that sent me the message. I can just have direct access to his address. So I say sender, I'm telling him something, and I'm telling you that you didn't provide enough coins. So it's not enough coins error is actually thrown straight back to the client, which I think is correct in this case, as I said, because he hasn't fulfilled his part of the contract. But if everything goes well, then I'm brewing my coffee, and I'm sending my coffee back to the client. Okay, so now let's try to run this and see See what happens. So everything went well. I'm inserting my coins, and the number of coins total is 2. I'm brewing the espresso, and I'm getting myself an espresso. Okay, but now let's do something more interesting then. Let's say that I'm inserting just 1 coin here, and then I say I want a latte. Okay, in this case I should really get a no coins error instead of a beverage, as I've already encoded in the coffee machine. Let's see. Yeah, this seems to work. I get myself an error. Please insert one more coin. So here, failure is actually thrown straight in the client. No, sorry, errors are thrown straight into the client's face, while failures should not. Right. So the interesting piece I think here now is now let's trigger a failure and see what happens. As I've already said, all actors that are created by other actors, which you have to, are like automatically supervised, and the default strategy is on a regular exception they are restarted. And the restart in the actor world means that the old instance is just thrown away. A new instance is created, reinstantiated, and handed out to serve the user. Okay. So what I want to do here, that I would like to insert one coin. Since I won here, then I'm inserting my missing coin, and then I'm triggering an out of coffee beans failure here. So I'm running out of coffee before I can brew, and then I say I want my latte, and then I'm waiting for my beverage. Okay. So now let's see. What I need to do first is that I need to make sure that I respond to this message. Let's see. What I'm doing here, I'm simply setting the out of coffee beans to true, and I'm also, let's see, I'm adding a check here. Oh, sorry. I'm adding a check here that if I'm out of coffee beans, I'm just going to throw a regular exception. Okay. So now, if I run this, you can see that the exception is thrown, and the client didn't get his coffee naturally. One thing that ARCA has though is we didn't actually see that things actually got restarted, but ARCA has a set of callbacks that will be called whenever the component is restarted. So we have like pre-restart, post-restart, pre-start, post-stop, and a lot of these things, right? So in this case, I'd like to, for example, add an implementation of this post-restart. So on this new instance, in this case, this will be invoked on the new instance. In this case, I'm just printing out restarting the machine and see that it's actually happening. You can see here it's actually restarted. So this is a fresh new instance that is ready to serve. However, the problem is that my context is lost. This new coffee machine has no idea who submitted this order, how many coins were there, and so on. So what I need a way to actually manage my context throughout this failure scenario. So the best way is doing, as I said, you should want to reify the full error. That means that's the place I'd personally like to put the context. There are many ways you can do it, but what I would like to do then is actually define and see. Oh, I don't know what happened now. I'm debugging. I don't want to do that. I want to actually define a semantically interesting failure. Instead of just throwing exception here and saying, oh, I'm adding actually an out of coffee beans failure here, or that extends exception, where I'm putting in my current customer. I'm also putting in my pending order here, and also the number of coins he has inserted, so nothing should be lost. But the important thing here now is, of course, I need to make sure that I capture this here instead of throwing an exception. So here you see I'm capturing the current sender of the message. That's the guy that is currently trying to get his coffee, his selection, and the number of inserted coins. And what I also need to do now, as I said, all supervisors are by sort of without you having to do anything, they supervise the component. But in order, I mean, all serious actor systems should actually make sure that they take full advantage of the idea that failures are just regular messages. They should be encoded as rich. They have rich semantics, right? You shouldn't just throw errors, exceptions around. You have really no idea what's happening. But you should really encode the failure in the supervisor so you can act accordingly to this specific failure. So you do that by overriding the supervisor strategy. And I'm not going to go through, I mean, there is some configuration here. You can see max number of retries within time range and stuff like that. But the important thing here is that this guy now responds specifically to this out of coffee beans failure. Here I'm just printing it out and restarting him. But this is also not sufficient, right? Because I need a way to get a hold of that context in the post restart. So I need a way to like grab the context and reinstantiate that on the new instance. And if you remember correctly, I had this where is it? This post restart method. And I'm currently not doing anything with it, but if we say that we do that here now instead, you see, because I'm actually getting past the actual failure here, right into that method, so I know what's going on, I know what happened, I know why things failed. I can also get a hold of the actual context here. So if it was an out of coffee beans failure here, I can do here again pattern matching. I can actually grab the current customer that was trying to get his coffee, his pending order, and his coins. And I can reinstantiate those here. And here's also a funky thing that's pretty nice. In ARCA, you can actually send things to yourself using the self-reference. So here I'm actually just resubmitting the pending order to myself, and with the customer as a sender. So I can sort of fake that I'm getting even though I'm sending myself the message, I'm the sender. I can actually put in the customer address here as the sender. And therefore, he should be when he does reply, he will just reply direct back to the original customer. So if I've done everything correctly here now, then we should see we shouldn't just get a failure and the client hanging there. But you can see when I'm actually restarting it here, I'm able to resubmit my pending order and start brewing my latte, and the customer actually gets his latte, even though the whole machine failed and a completely new one was reinstantiated. The client didn't even notice, right? And this is sort of the power of full isolation, having failures reified as messages being notified outside in a safe context, right? That's healthy, that can manage the failure. And the very cool thing, I don't have much time left. I was going to like take this now to the distributed world in just a few slides. But I can just say that the interesting thing is this model just works exactly the same across machines with exact same semantics. Since everything's messages are there asynchronously sent. The only thing that will change is the latency of getting messages across machines instead of across cores. So here you really have, if you really embrace this way of thinking and this way of designing your systems, I believe that you have a model that actually works very well across all deployments. I mean, starting on a single core system, growing it onto multiple machines, multiple data centers, the failure model and the way of thinking about failure is the same. So I'm just going to go back to my slides. I'm just going to jump forward a little bit here. So, in summary here, we've covered a lot of things, but one of the most important lessons here is like complex systems, like I think most of you probably are writing, always run as broken systems. They always run in degraded mode, to quote Richard Cook. And I really believe that resilience is truly by design. We just can't hand-wave it any longer. Try and bring in additional stuff to solve it, right? We build our system and then we just add stuff. Turn on clustering, I don't know, in WebLogic Server or Tomcat, or like, add things. No, we need to start like truly simplify and be true to what's really going on and have a model that actually works from small to large, essentially. And I really believe that without resilience, nothing else matters. That's where it starts and ends. Okay, so thank you. That was everything I had.